why don't we get started? For the rest of the day, we're going to return back to using the prover, and we're going to do a couple of things. The next segment here, we're going to hit a few points. So the first thing I want to do is just one more little feature of the prover that lets us write another kind of property, which we call a hyperproperty. After that, I'm going to talk about our process for designing a specification. So far we've talked about here's what the prover can do and here's how to use the prover to do that. But then the question is, what should you do with the prover? If I get a new smart contract, how do I decide what properties to write? So we'll spend a chunk of time on that. And then the third thing I want to do is introduce the AAVE governance token. So the plan is that will be an exercise in designing specifications. And so we'll think about that over lunch. I'll have you guys think about some properties. After lunch, we'll come together and discuss some of those properties, and then we'll have a work session where you can apply what we've learned today and yesterday to try and do some verification for the AAVE token. So that's the plan. So let's jump in. So a useful feature and something you often want to do when you're writing a property is to not just execute your program once, but to execute it twice, to do two different sequences of operations so that you can compare the results. So for example, you might like to write a property that says something like two small deposits give you the same result as if you did one big deposit, right? So if I deposit A, then deposit B, that should be the same as if I deposited A plus B. Other examples that come up often are adding permissions doesn't cause reverts. So if I was allowed to do the operation before, and then we add a new permission, I should still be allowed to do the operation. And similarly, removing permissions shouldn't increase the number of operations that succeed. A third sort of more financial property is if you have a contract where you stake some money, and the more you stake, the more you should earn. That's a property that's comparing hypothetical executions, right? One in which I stake less, one in which I stake more. And similarly, if I stake and stake the same amount, but stake it for a shorter or longer period, we might want to give guarantees about that as well. So these are all properties that compare one hypothetical sequence of operations with another hypothetical sequence of operations. Okay. And the way that you can write these kinds of properties in CVL. And the way you do it is you sort of save the state of the world. So we have a special storage type. And then later you can go back to that previously saved state. So for example, to check this first one, and we'll actually go through this example on the next slide, we save the state of the world, we do our two small deposits, and then store the balance. And then we restore to that initial state of the world and then do our one big deposit. Now we have another balance, and we can compare those two. Okay. There's a special variable called last storage, and again, I'll show you on the next slide how this is used, but that's the thing that you save. And then there's a syntax for resetting back to that saved storage, and then executing a function. So let's go through an example. So here, this is a similar to deposit A and then deposit B is the same as depositing A plus B, except I did it with transfer. So the rule here, what's intended to prove is if I first transfer A tokens and then I transfer B tokens, that should be the same as if I transferred A plus B. And this looks a lot like the kinds of rules we saw yesterday. So in order to call transfer from, we're going to need a sender, we're going to need a recipient, and we're interested in the amounts A and B, so we have variables for those. All right. Let's skip over this for just a second. We want to talk about what happens if we first transfer A and then transfer B. So we call transfer from with amount A, and then we call transfer from again with amount B. Okay. And then we can store the balances of the sender and the recipient. Okay. So this is our first hypothetical execution, and it started in this last storage that we see in the init variable. So once we've done our first hypothetical world, we can then use this @init syntax to reset back to that initial saved storage. Okay, so that's what this @init does. it says run this method, but before you do that, rewind so that the state of the world is the same as it was at init. So then we call transfer from again, same sender, same recipient, but now we're transferring the sum. Okay? And once again, we're recording the balance of the sender and the balance of the recipient into these variables. Right? So now we've recorded the effects of these two hypothetical executions, and so we can compare them. Right? So finally, we have here our assertion. We can assert that the balance of the first sender is equal to the balance of the sender in the first execution is the same as the balance of the sender in the second execution. And similarly, we can assert that the balance of the recipient in the first and the second executions are the same. Okay? So I'm not going to go through and do an example on this. It's a useful feature, and it is a useful thing to keep in mind that you can do when you're designing properties. But I think it's a pretty straightforward set of features. Any questions about this sort of different hypothetical world kind of rules? Okay, so let's move on. So now I want to talk about the art and science of designing specifications. So yesterday, we spent a lot of time learning how to write specifications. We saw how to put rules in the Certora verification language, and we saw a variety of different kinds of rules and how to debug them. So that's really the how. How do I write specs? But now let's talk about the what. What specs should I write? So if a formal verification is only as good as the specs that you're verifying against, right? If you write a stupid spec, right, maybe you just have a spec that says true is always true, or 7 is always greater than 5. You can verify that, and you'll get a nice green check mark, but it doesn't tell you anything about your program, right? So it's important to think about all of the interesting behaviors of your program so that you can actually make sure that you check that your program satisfies those behaviors. Chandra talked a little bit this morning about mutation testing, and that's one way to give you a good sense of whether you've written a good spec or not. Right? So there, the tool we have will change your program a little bit. If you introduce a bug and your spec doesn't check it, that means your spec is not catching all the bugs. Right? So that's what the mutation testing idea is. But even before you've written your spec, it's nice to sit down and write down, here are the things I want to check, so that you can make sure that you do have good coverage kind of from the beginning. Okay? So what I want to do now is talk about several different kinds of rules, and each of these sort of gives you a checklist of, let me just list all of the unit test rules, and that's fairly systematic. Let me list all of the variable relationships. Let me list all of the variable changes. Each of these categories is a kind of rule, and many of them, there's sort of a systematic process you can go through to make sure that you've checked your entire program. Okay? So I'll go one by one through these different kinds, and then we'll come back and summarize. So the first style of rule we like to call unit test style rules. Now these are already infinitely more powerful than unit tests. We saw these yesterday. They're infinitely more powerful because we're going to check the behavior of functions on arbitrary inputs instead of on specific inputs. But they're very easy to write because you've usually, most contracts in their documentation already tell you exactly what the properties are for each method. Okay, so if you look at an interface, it'll usually have some comment above each method that says, here's what the method should do. Here's what the arguments are. Here's what effect the method should have when you call it. Here's what the method should return. And sometimes, here's the conditions under which it should or should not revert. Right? So these are all properties of a method, and if you've ever written any code, you've probably at least thought about these and hopefully written them down in your interface. So this gives you a very nice place to start if you want to write a specification, because you can just take the English description in the comment and turn it into a rule. Okay? So we saw how to write these kinds of rules yesterday, so I'm not going to go into the details. But just as an example, yesterday we looked at the comment for the transfer method, and it says transfer should transfer amount of tokens from the sender to the recipient. So we then proved a rule that said transfer reduces the sender's balance by the amount, And then transfer increases the recipient's balance by amount. Okay? And we also did rules yesterday about when transfer does or does not revert. Okay? So to do these, to sort of come up with a list of unit test style rules, you can just look at all the methods in your contract, all the public methods, especially the non-view methods, and just say, what is this supposed to do? And then write a rule that does, calls the method and checks that it does what it should. There's a nice tool in the Certora prover that I want to show you briefly that actually can be helpful with this occasionally. So let me just flip over to that momentarily. So every time you do a verification in the prover, in addition to the output that we were looking at yesterday, there's this nice little tab which is the contract list. This shows you all of the contracts that went into the verification. And as part of that, there's this little method section where it actually lists all of the external methods. So this is a nice, easy way to get a list of methods. And then if you want to systematically write unit test style rules, you can go to each of these methods and say, is there something interesting to say about this method? Okay. So one other thing I'll mention, in practice, the documentation is often incomplete. So I suggested go look at the comment and then write a rule that does what it says. But really what you should do is go look at the method, read the comment, but then write rules that check that the methods have the effects they should have, and that they return what they should return, and that they revert when they should or don't revert when they shouldn't. That's not always all written in the comment. So you should think about that if you're looking at a contract that you didn't write, and maybe even submit a PR to whoever wrote the contract by adding a comment. They will appreciate it. Question?
And then there was a talk by Joran, and he said, what are the auditor's approach? And he said that there are the auditor's approach that start from the code, and there are the auditors that start from the spec. It sounds like there is a risk. If you look into the code, you get contaminated. So maybe actually you don't want to do what you're doing. I'm just thinking loudly.
Yeah, let me repeat the comment for the stream. So what Muli said is, in a previous talk in the DeFi 101 workshop last week, it was pointed out that sometimes some auditors look at the code to start, other auditors look at the specification to start. And Muli said, well, maybe we shouldn't be looking at the code because then you're sort of getting the bugs from the code into your head before you write the spec, and so then you'll write a spec that misses those bugs. That's actually not what I'm suggesting here. I'm suggesting to look at the documentation for the code rather than the implementation. So while you're writing your specs, and actually we did this yesterday, there were very few places where we ever looked at the code. What we did is looked at the interface file, right? The interface doesn't tell you any of the implementations. It just says, here's the methods, here's what they're supposed to do. And interfaces correspond very closely with specifications. So it's great to look at the interfaces and to think about them. And it's good wherever you can to avoid looking at the code. The time when you look at the code is when you get a violation and you want to see what's actually going on with this violation. But when you're designing the specs, you should focus as much as you can just on the interface. So thanks, Millie. That's a great point. Okay, the second kind of, or two kinds of rules that I want to talk about are variable relationships and variable changes. So variable relationships talk about the relationships between different fields in your smart contracts. Okay? And the way you get these variable relationships is you look at your smart contract and you look at pairs of variables and you say, are these related? Should I know something about this variable based on that variable? So as an example yesterday, we said for an ERC20, the total supply should be the sum of the balances. And in the contract, there's a variable called total supply. There's a mapping called balances, right? And we can look at those two variables and say, oh yes, of course they should be related. And that suggests a rule that we can then write that relates those two things. Okay, and most of these relationships end up being invariants, and so you can write them using CVL syntax for invariance. And one thing I'll point out here, there are more variables. If you're verifying a contract and it refers to other contracts, there are also variables in those other contracts. And so it's sometimes important to think about not just the specific contract you're verifying, but related contracts. Just as an example, a solvency rule might say if I have a bank, right? The bank is holding some amount of tokens, and the bank has a variable that says how many tokens it thinks it's holding. But the actual amount of tokens are stored in the contract for the token. And so you might like to write an invariant that says the variable that says what the bank thinks it's holding is equal to the actual amount that it's holding, according to the other contract. And you can write these kinds of invariants. In CVL, I haven't talked about it, but there's a good section of the user guide on how to set up multiple contracts, so I'll refer you to that. Another thing, as you're looking at the fields of the contract, another kind of rule you can think about are what we call variable change rules, and we also saw examples of this yesterday. To come up with a variable change rule, you look at a single variable and say, if this thing changes, what should the conditions be, right? So yesterday we did an example where we looked at the allowance, and we said if an allowance changes, or we actually focused on if an allowance gets increased, and we proved that that should only happen if the owner of those funds called one of the specific methods that increases the allowance. Okay? So this is a good way of, again, generating a set of rules, is just asking yourself, when I see a variable, how should it change? And there's kind of a template for these kinds of things. These rules in general, you store the value before, you do an arbitrary operation. So we saw yesterday that this syntax says, go call any contract method with any arguments. And then you get the value after. And then you just assert that if the value changed, then whatever your description of what you should know should be true. Okay? All right. So these are another couple of systematic ways to come up with specifications. One of them is look at pairs of variables and think about how they're related, and one is looking at individual variables and thinking about under what conditions they can change. Okay. The next kind of rule I want to talk about are a little bit more abstract, but they're often a useful way of thinking, and that's state transition diagrams. So a lot of smart contracts, or parts of smart contracts, have a kind of flowchart feel. What do I mean by that? They have some notion of state. So for example, there might be, this corresponds to like a proposal, right? So a governance proposal, it might start off not existing, and then you propose it, now it exists, right? And then there's some voting period, and then at the end of the voting period, somebody calls close. And depending on whether there's enough votes or not, it will either get accepted or rejected. And once it's accepted, you're allowed to call execute, and then it will become executed, and then you're not allowed to do anything with it at that point. So this sort of describes how the state of the contract can evolve, but you're sort of grouping things together into these sort of bigger states. Okay. So these state transition diagrams, if you sit down and you think about your contract and you say there's a natural sort of flow or progression of events, ways that the state can change, that gives you another really good way of designing properties. Okay. So there's a couple of pieces of this. So one is it's useful to look at individual states and say, what are all of the things that I should know in a particular state? Or how do I know that the contract is in this state? So for example, I might know that the contract is uninitialized if the initialized variable is 0. So I might write that here. I might know that the proposal has been, the governance proposal has been proposed if initialized is non-zero and maybe there's an executed, maybe there's an executable that gets set, right? So there's different things that must be true in each of these states. How do I know that it's accepted? Well, I know that it's been closed and that there's enough votes. And I also should know that it has the executable and that it's been initialized, right? So for each state, you can say, for all of the variables, how do I know whether the whether the contract is in that state or not? There's a feature of CVL, which I didn't describe yesterday, but it's just a nice little shorthand, which is a definition. And this is just like defining a short function. And so you can write a definition, accepted state, as an example here, that takes in some parameters and returns some value. And the way definitions work is you just give an expression, and then every time you write accepted state of E, it just plugs this in, just like any function in any programming language. But when you're thinking about state diagrams like this, it's useful to write a definition for each state. So here I've given an example of the definition of the accepted state, and the expression here is it's accepted if it's initialized and the executable is non-zero and the votes for is greater than the votes against and the block timestamp is after the deadline, something like that. So you can list here the properties, or you can write a condition that tells you when you're in a state or not. Once you've done that, you can then there's a nice invariant you can write always, which is the contract is in exactly one of these states. Okay, and that often is a good kind of invariant because it catches places where, for example, if you know two things in one of the, you should know two things in one of the states, but you only remember to change one of them, then the contract will not be in this state because you've changed one of the things, and it won't be in the start state because you've changed another thing. So this gives you a nice invariant. And the other kind of thing that you can do is check that the transitions are appropriate. And so for each of the transitions in your diagram, just like we did with variable changes, you can write a rule that says if the state changes from here to there, then it must be because I called the appropriate method, or the time has elapsed, or whatever it is that the conditions are for making these transitions. Okay, so popping up a little bit, when you're writing a set of rules, it's good to try and identify if there's a state transition diagram that corresponds to your contract or to a part of your contract. If there is, draw yourself the diagram, describe what you know in each of the states. You can write definitions for those. Then you can write an invariant that the contract is in exactly one state, and you can also write state change rules to check that the transitions happen appropriately. Okay. The next style of writing rules is a little less systematic, but is still quite useful. And in fact, this is often a good place to start. So I don't necessarily do things in this order. A stakeholder rule just means I'm putting myself in the perspective of one of the users of the system, right? So maybe I have some liquidity pool, and so I have some users want to use the liquidity pool to swap one kind of token for another, and so I might want to think about what their requirements are. I may have other users who are providing liquidity, and so I might want to put myself in the shoes of a liquidity provider and say, what do they care about? And then once I have that sort of user story of, or maybe, the bank's user story is the thing that would go bad is if somebody took all the funds out of the contract. Or if I have a bank, an end user of the bank who's depositing, withdrawing funds, their sort of bad story would be they deposit some funds, wait a while, and then they can't get their funds back, right? That would be a bad situation. And so putting yourself in the shoes of particular stakeholders gives you a set of horror stories, and then you can take those horror stories and turn them into properties that say this bad thing doesn't happen. And often these generate a couple of rules that sort of work together to tell the whole story. So in the example of a user who wants to be sure that if they deposit, they can later withdraw, the way you would prove that is you actually have to think about all of the methods that would happen starting from the deposit, ending with the withdrawal. So one of the things you care about is if you deposit, you get a balance. So that's one rule you can prove. I call deposit, my balance goes up by a certain amount. Another thing you might care about at the end is when you withdraw, when you call withdraw again, your balance should go back up, or not your balance. Your balance in the bank should go down, but your tokens, you should get the tokens back, right? So that's an important thing, is that you can call withdraw and get your tokens back. But the question is how many tokens, and the answer is whatever your balance in the bank is. So in between when you do the deposit and when you do with the withdraw, you want to make sure that your balance isn't changing if it shouldn't, right? And so that suggests a rule that your balance shouldn't go down unless you call withdraw or maybe transfer or whatever. And then the last piece here, the thing that another way that this could go wrong that you wouldn't be able to withdraw is that the withdraw method just always reverts for some reason, right? So all of these taken together kind of are the parts you need to rule out this bad situation where you deposit some tokens, wait a while, and then try and withdraw, right? And by breaking this into these kinds of rules, you're also kind of handling different cases where other people are calling, functions in between. So you could just write a rule where you deposit, and then you call withdraw, and then you assert that it works, right? But that doesn't account for other transactions coming in between the deposit and the withdrawal. Okay, so this stakeholder perspective is a really good way of writing rules. There's no place in the code you can look and say, tell me what all the stakeholders are and what all of their requirements are. The place that you might look is in the advertising for the protocol, right? The advertising for the protocol says if you stake more, you earn more. Well, that gives you a nice stakeholder rule, which is if I stake more, I earn more, right? Or advertising for a token might be, this token is secure, you're not going to lose all your funds. Well, that gives you a nice stakeholder rule, right? You can prove that you're not going to lose funds. So this is a useful perspective when you're writing rules. You kind of just think about who are all the people who are using the system and what do they not want to happen. The last kind of property I want to talk about are what we call high-level rules, and these are even a little more abstract than the stakeholder rules. So the idea behind these high-level properties is to forget about the details of the system. Think about an abstraction, right? So just look at the methods in your contract as sort of arbitrary mathematical formulas and think about what properties they should have. So what do I mean? So for example, you might look at two getters and say if this one goes up, that one should go up, right? You're not focused in like some of the other rules on exactly how much it goes up by, right? You're just saying, these two things should increase together. They should be correlated, right? Or you might say if this thing is 0, that thing is 0, right? Not saying anything about the other conditions, right? Or exactly how they should relate to each other. It's just saying if one thing's 0, another thing's 0. So you're sort of forgetting a lot about the system and just checking some very basic kind of sanity checks here. Another kind of thing, we saw an example of this when I was talking about hyperproperties, is if I do two small operations, I get the same answer as one big operation. Or if I have multiple ways in my contract to do the same thing, then I should get the same answer. For example, transfer from, if you give it the message sender, should be the same as transfer, right? They should do the same things. They're just different contexts where they apply. So these kind of high-level properties, they seem less powerful, right? Because they're saying less about the contract. They're just, giving some sort of high-level, not very detailed information. But the advantage of these kinds of properties, there's a couple. So one is they're a good way to get good coverage quickly. They're easy to write these kinds of rules. You have to be a little creative, but these kinds of templates get you a way to think about them. But you can very quickly get good coverage. And these kinds of rules do find bugs. So if you guys went to Nurit's DSS talk on Sunday, she gave an example of this where we found a bug in Sushi's Trident protocol. And the way we found that bug is we just said it was a liquidity pool where there are liquidity providers who hold tokens, and then there are collateral tokens that you can swap one for the other. And all we said is that if the liquidity provider, if there are any liquidity tokens, then there must be collateral tokens as well. So you can't have liquidity if there's no liquidity in the pool, and there can't be liquidity in the pool without it belonging to somebody. And it turned out that this rule failed and uncovered a bug that could drain the entire pool, because you could actually get into a situation where somebody could withdraw the collateral tokens without providing liquidity tokens, and then they could use that exploit to drain the pool. So these properties can sometimes get you good coverage, get you interesting, find interesting bugs, without having to drill down and really understand all the details of exactly what each method should do. The other advantage of these high-level properties is that when you're writing them, you're thinking about your contract in a different way than the developer of the contract probably is. And I think there's a quip that formal verification is the art of making sure that your program and your specification have the same bugs. If you're thinking about your specification in exactly the same way you're thinking about your program, you might end up making your specification match your program exactly, and you'll have the same bugs. These high-level properties are a different way of thinking about your program, and so sometimes they'll turn up bugs that a low-level focus can lead you to miss. Okay. So just to summarize, we went through several different kinds of properties. So unit test style rules, the way you write them, you describe the expected behavior of each function. To think about variable relationships, you look at pairs of variables in your contract and think about how should these variables be related to each other. And you look at individual variables and say, under what conditions should these change? We talked about state transition diagrams. There you think a little more abstractly about your protocol and say, what are the states that the contract can go through? And then that lets you first specify the states and make sure that you're consistent about how you use them. And secondly, describe the conditions when the transitions happen. We talked about stakeholder rules, which is putting yourself in the shoes of a stakeholder and thinking what's the worst thing that could happen, and then designing rules to rule those bad things out. And lastly, we talked about high-level properties, which is to think abstractly about your functions, not try and dig into the details, but just give very high-level properties that they should satisfy. And that's a more abstract kind of thing, but can get you going quickly and can find unusual bugs. Okay. Next section. So what I want to do next is take some of these ideas. I'm going to describe a real contract to you guys. It's a fairly simple one, but it has some nice properties. And the goal of this is an exercise, and this is the exercise we're going to work on in the afternoon. So I'm going to explain the contract and show you where to get the interface. And then the exercise is look at the interface, come up with some properties, and then after lunch, we'll come back and discuss those properties with each other, thinking about them in terms of the framework that I just laid out. And then you guys can implement those properties. Okay. So the AAVE token is used for controlling the AAVE protocol. Okay. So it's an example of what's called a governance token. And what a governance token is it's a token that comes with some kind of voting power. Okay? So the idea is if you hold AAVE tokens and there's a proposal on how to change AAVE or what AAVE should do, you can use your tokens to vote for or against that proposal. Okay? And the more tokens you hold, the more votes you get. Okay? So this is both an ERC20 token. It has methods like transfer so that you can send your AAVE token to somebody else. But it also has additional methods for doing voting. Okay? And with the AAVE token, one of the important features it provides is the ability to delegate your vote. So if you hold some AAVE tokens, you can say, I want to use those tokens. I want to just allow somebody else to vote with those tokens. So the things you can do with the AAVE token, you can delegate the voting power to somebody else. You can't redelegate. So if I delegate my token, my voting power to you, and then you delegate to somebody else, they don't get my voting power, they only get your voting power. Okay? So just as an example here, if I have Alice, Bob, and Chuck, if Alice delegates to Bob, her 10 tokens go to Bob. If Bob delegates to Chuck, his 7 tokens go to Chuck, but the 10 that Alice delegated to him does not also go to Chuck. He still has that voting power. If Chuck delegates back to Bob, Chuck's 5 tokens go into Bob's delegating power. So with this diagram, Bob has both Alice and Chuck's voting power, and that's why he has 15. Okay. We say a few more things. One is the token has 2 different kinds of voting, so you can vote on proposals. You can vote on proposals, and you also can use your power to vote on propositions, whether to even consider them or not. There's a concept of meta-delegation. You don't need to worry about it too much. It's a mechanism for allowing somebody to control their votes without actually having to call Ethereum methods. It uses digital signatures for that. And as I mentioned, the contract's in ERC20, so you can transfer these tokens and keep track of ownership. Okay? So the exercise, as I said, is going to be to look at the interface and write some properties, and we will do that after lunch as suggested. So let's break for lunch now, and then when we get back, we'll talk about properties.